To obtain an isolated grounded 120/208 three-phase system without installing a completely new grounding system, consider these options. Firstly, utilize an isolation transformer. Install an isolation transformer at the panel board with a 120/208 volts three-phase secondary. The transformer's primary side should be connected to the existing grounded system, and the secondary side will then provide the isolated ground reference. Secondly, you can employ a delta-wye transformer, also known as a Scott-connected transformer. Install a delta-wye transformer, which effectively creates a grounded center tap. Connect the transformer's primary side to the existing grounded system. The secondary side will provide the isolated grounded neutral. Thirdly, leverage ground fault circuit interrupters, or GFCIs. Install GFCIs on all branch circuits that require isolated ground. GFCIs monitor the current flow between the hot and neutral conductors and trip if a ground fault is detected. Fourthly, you may utilize a grounding isolation kit. Purchased grounding isolation kits can be installed on the panel board to create an isolated ground reference. These kits typically include a ground fault sensor and isolation transformer. When selecting and implementing any of these options, there are several additional considerations that you must address. Firstly, electrical code compliance is crucial. Verify that the chosen solution complies with the National Electrical Code, also known as the NEC, and all applicable local regulations. Secondly, ground loop mitigation is very important. Implement appropriate measures to prevent ground loops between the isolated ground and the existing grounding system. Thirdly, proper electrical isolation must be ensured. Ensure that the isolated ground is electrically separated from the existing grounding system to maintain the integrity of the isolation. Regarding electrical code compliance, be aware of the requirements outlined in the National Electrical Code, or NEC. Article 250 covers grounding and bonding, and it is crucial to adhere to these regulations to ensure safety and proper system operation. Specifically, review Section 250.96 Bonding Other Enclosures, which addresses bonding requirements for metal enclosures and raceways. Section 250.146 Connecting Receptacle Grounding Terminal to the Equipment Grounding Conductor provides guidance on connecting receptacle grounding terminals in specific situations. Section 517.13 Healthcare Facilities addresses grounding requirements in healthcare settings which often require isolated power systems. When implementing an isolation transformer, several factors must be considered. Firstly, transformer sizing is paramount. Calculate the appropriate transformer size based on the load requirements of the isolated system. Oversizing the transformer can lead to inefficiency, while undersizing can result in overheating and failure. Secondly, insulation class must be considered. Select a transformer with an appropriate insulation class for the operating voltage and environmental conditions. The insulation class indicates the transformer's ability to withstand thermal stress and prevent dielectric breakdown. Thirdly, impedance is a critical parameter. A transformer's impedance affects the system's fault current levels and voltage regulation. Choose a transformer with an impedance that is suitable for the application. Fourthly, the core type influences performance. Different core types, such as laminated steel or toroidal cores, offer varying levels of efficiency, noise, and size. Select a core type that meets the specific requirements of the application. Delta-wye transformers also present unique considerations. Firstly, phase shift is inherent in delta-wye transformers. The secondary voltage is shifted by 30 degrees relative to the primary voltage. This phase shift must be taken into account when connecting the transformer to other equipment. Secondly, harmonic mitigation can be achieved with delta-wye transformers. The delta connection can trap certain harmonic currents, preventing them from propagating to the primary side of the system. Thirdly, the neutral point is crucial in Y connections. The grounded neutral point provides a stable reference for the secondary voltages and is essential for proper system operation. Fourthly, the turns ratio determines voltage transformation. Select a transformer with a turns ratio that provides the desired secondary voltage from the available primary voltage. Ground fault circuit interrupters, or GFCIs, provide essential protection against ground faults. Firstly, sensitivity is a key parameter. GFCIs are designed to trip when a ground fault current exceeds a specific threshold, typically 5 mA. This sensitivity ensures that even small ground faults are detected and interrupted. Secondly, response time is critical. GFCIs must trip quickly to prevent electric shock. The response time is typically in the range of 20 to 40 milliseconds. Thirdly, testing is essential for GFCIs. Regular testing is necessary to ensure that the GFCI is functioning properly. Test buttons are provided on GFCIs for this purpose. Fourthly, location is important. GFCIs should be installed in locations where ground faults are likely to occur, such as wet or damp environments. Grounding isolation kits offer a convenient way to create an isolated ground reference. Firstly, ground fault detection is provided by these kits. Ground fault sensors monitor the current flowing in the grounding conductor and trip if a ground fault is detected. Secondly, isolation transformers are often included in these kits. These transformers provide electrical isolation between the isolated ground and the existing grounding system. Thirdly, surge protection may be integrated into these kits. Surge protection devices can help protect sensitive equipment from voltage surges and transients. Fourthly, ease of installation is an advantage of these kits. They are typically designed for easy installation on existing panel boards. When addressing ground loops, there are several mitigation techniques to consider. Firstly, single-point grounding is a common approach. Establish a single point in the system where all grounding conductors are connected. This prevents circulating currents from flowing in the grounding system. Secondly, fiber optic isolation can be used to isolate communication cables. Fiber optic cables do not conduct electricity, so they can prevent ground loops from forming between different pieces of equipment. Thirdly, isolation amplifiers can be used to isolate analog signals. Isolation amplifiers provide electrical isolation between the input and output signals, preventing ground loops from interfering with signal transmission. Fourthly, shielded cables can reduce electromagnetic interference. Shielded cables can help prevent noise from coupling into the grounding system. To ensure proper electrical isolation, several techniques can be employed. Firstly, insulated conductors are essential. Use insulated conductors for all wiring to prevent unintentional grounding. Secondly, isolation barriers can be used to separate different grounding systems. Isolation barriers provide a physical separation between the isolated ground and the existing grounding system. Thirdly, dielectric testing can be performed to verify the integrity of the isolation. Dielectric testing involves applying a high voltage to the insulation and measuring the leakage current. Fourthly, impedance measurements can be used to assess the isolation between different grounding systems. High impedance indicates good isolation. Remember, the implementation of any of these solutions should be performed by a licensed electrician with proper safety precautions. This ensures compliance with electrical codes and safe operation of the system. When dealing with existing building infrastructure, especially in a high-rise building, several additional factors come into play. Firstly, existing wiring can affect the choice of grounding solution. The age, condition, and type of existing wiring can influence the feasibility and safety of different grounding methods. Secondly, structural limitations can pose challenges. The building structure may limit the available space for installing new equipment or running new grounding conductors. Thirdly, accessibility is a key consideration. Gaining access to the electrical panels and wiring in a high-rise building can be difficult, especially in tenant-finished spaces. Fourthly, coordination with building management is essential. Any electrical work in a high-rise building typically requires coordination with the building management to ensure compliance with building codes and regulations. Furthermore, the presence of other electrical systems in the building can affect the grounding strategy. Firstly, shared neutral conductors can create complications. Sharing neutral conductors between different circuits can increase the risk of ground faults and voltage drops. Secondly, emergency power systems must be considered. Emergency power systems, such as generators and UPS systems, have their own grounding requirements that must be integrated into the overall grounding plan. Thirdly, fire alarm systems often require dedicated grounding. Fire alarm systems are critical for life safety, so their grounding must be carefully designed and installed. Fourthly, data and communication systems are sensitive to noise and interference. Data and communication systems require clean grounding to prevent noise and interference from affecting their performance. In addition to the specific techniques and considerations mentioned above, it is important to follow some general best practices for electrical work. Firstly, always to energize circuits before working on them. This is the most important safety precaution to prevent electric shock. Secondly, use appropriate personal protective equipment, or PPE. PPE, such as gloves, safety glasses, and insulated tools, can help protect against electrical hazards. Thirdly, follow lockout/tagout procedures. Lockout/tagout procedures ensure that circuits remain energized while work is being performed. Fourthly, inspect tools and equipment before use. Inspect tools and equipment for damage or defects before using them. Fifthly, never work alone. Having another person present can provide assistance in case of an emergency. Sixthly, be aware of your surroundings. Pay attention to potential hazards in the work area, such as wet floors or overhead obstructions. Seventhly, never take shortcuts. Shortcuts can compromise safety and lead to mistakes. Eighthly, consult with a qualified electrician if you are unsure about any aspect of the work. Seeking expert advice can help prevent costly errors and ensure safety. By carefully considering these factors and following best practices, you can safely and effectively obtain an isolated grounded 120/208 three-phase system in an existing building without installing a completely new grounding system.